All right, good morning. We had a short break, but we have to keep working. So we have a couple of weeks left. We will do first some announcements. So there is a lab for this week. The lab is on the a little bit ambitious side. So if people don't want to do it, you can skip it. It covers some of the distributed computing concepts with Redis and ZeroMQ. Redis and ZeroMQ, I will talk a little bit after the first part of the lecture, but you will have to kind of study it a little bit on your own. So that's why it's a little bit ambitious. So the task for this week is to work in groups, study a little bit of Redis and ZeroMQ, and create a distributed chat. So you basically have a chat client, you connect to a broker, and then you can chat with other clients which are connected to the broker. And the infrastructure with the use of ZeroMQ is very simple because ZeroMQ already offers a concept of a node and a concept of joining and of broadcasting messages. So all you need to do is to wire it together and design a protocol of how you will send and receive messages. So conceptually, it's not super hard, but it is something new. Like you haven't done it before, so it is on a challenging side. And then Redis is a key value store. So it's sort of like a database where you say, for this key, I want to store this blob or this JSON or this binary data. And then you can retrieve it. So every time you store something, it's kind of like hash table, but in a distributed way. So in a sense, all the clients, like you have a hash table in your code and you're saying, give me the object for that key. In Redis, it's pretty much the same, but you're doing it on the process level. So you have multiple clients asking the Redis hash key value store to give keys for a particular value, to get value for a particular key. And then if there is none, any client can store something there. So you can use it for keeping a history of the chat. So if you join a chat which was going on for a while, you can sort of retrieve all the history because the history is stored in the key value store. Those two concepts are super useful. You're probably gonna use them for your bachelor thesis. So if you practice a little bit this year, you will have a better start next year. But they are super useful in many different domains and many different applications which you build. Even if you're doing like an online shop or anything with web services with Christopher in a cloud course, very often we have to cache certain things such that we don't have to compute it again or we don't have to look it up again. Then Redis is a fantastic solution. There are other key value stores. Redis is just one example, but there are other ones which follow the same principle. So you can use later on any of the other ones. And then ZeroMQ is quite unique because it's a messaging bus, but without the infrastructure. So what does that mean? It means that you only have nodes and you're creating the infrastructure yourself. So there are other messaging buses like RabbitMQ, for example, and you bootstrap the server and then you initiate the clients and the server creates the infrastructure for you such that two nodes can talk to one another, but the infrastructure is created by the server that you instantiated. The advantage of the server instantiation is that you have persistence. So for example, if two nodes want to talk to one another and this node goes down, the message goes to the infrastructure, it's stored there, and when the client comes back, it gets the message, right? With ZeroMQ, you don't have the infrastructure. So if this client wants to send a message to this node wants to send a message to this node, and this node goes down, there will be no possibility of sending a message, right? So you will have to wait. So the message will be kind of sent, but it will not be delivered until that client goes up. But if this client goes down and this one goes up, then this one will not get it because the sending part is missing, right? So you will need to have both at the same time for the actual handshake to happen, right? But in the code, it's quite nice because what happens in the code is you have two nodes up, this one goes down, you say send a message, the message is waiting. This one comes up, the message is delivered, okay? Another scenario, this one is up and this one is up. This one goes down, that says send a message. Then this one goes down, this one goes up, nothing happens. This one goes up, the message is sent, right? So it's kind of, it's robust enough that for many situations, it is acceptable to deliver the message when the co-occurrence of the two things kind of happen. So ZeroMQ allows you to do this and allows you to play with client server or with broadcast or publish subscribe. So there are some typical patterns that you use with ZeroMQ, and you can sort of explore it. It's not rocket science. It's pretty simple. Like if you read the documentation for Redis and for ZeroMQ, you will get it. But it's a little bit of new concept. So you will have to dive a little bit into this. We're going to spend a little bit more time after the lab, but the lab is sort of a preparation for you to be able to kind of dive in a little bit more complex scenarios. So let's see how it will go. If it's too hard, then just drop it. Like there is no big deal if you don't do it. The lab is group work, so you're supposed to work in groups because it's a distributed setup, so it's nice to have multiple clients. So like organize yourself in some sort of small groups, at least like 3 people, because then you can work, like you can test easily because you can set up a single Redis server for yourself on one laptop and then use the other ones as clients and try to use the chat. I don't know if you've done like client server type of messaging with sockets in the operating system course with C. Did you use sockets directly? Did you ever use sockets directly in networking? Like to program a client and a server connecting to a socket? No? All right, so then it may be a little bit too hard because the ZeroMQ is kind of the same, like you're opening like connection sockets. So maybe I will extend the deadline and we talk a little bit more next week. So we will make this lab like 2 weeks. So that may be a bit better to explain some of the things. All right, so I will make this lab 2 weeks instead of 1 week, and we spend some time to catch up with some fundamentals next week if I don't manage to do it this week. All right, so that's this lab. An important thing is that next week lab is an oblique for Rust, and we will do it in the class. So you will have to be in the class. If people cannot come to the class, then let me know. You can kind of we will organize something if your physical presence is not possible, but preferably I would prefer people to come and we have it over with, right? So next week is like a lab which we will do in the class, and it will be a last oblique for Rust, and that's it. We'll have no other obliques. So this lab is a little bit ambitious. You don't have to do it. The oblique lab everybody has to do. It's for Rust. And then there will be 2 more labs. And they will be on the ambitious side as well. So there is no more easy labs apart from the next week obligatory lab, which will be easy. The other 3 labs, this one and the other 2 labs will be on the ambitious side. You don't have to do any of them. Like you can, happily pass the course without doing the ambitious labs. If you are ambitious and you want to do ambitious labs, pick your battles, and you don't have to do all of them. You can just pick 1 or 2, but you don't have to do all of them. So the ambitious labs are diving into different topics. This one is about distributed computing and kind of various architectures for connecting multiple moving parts. The next one will be about programming languages. We will extend the calculator. And there will be one which will be about more advanced programming techniques. So one about distributed computing, one about programming languages, and one about more advanced programming techniques that we sometimes have to use. So those are the upcoming labs. And then the easy lab for Rust, it will be something like pretty much straightforward, just for having us to get the obligatory task done. I haven't managed to do the CSAMs yet, so I will do it hopefully today and tomorrow. So for all the labs that has happened before, I will kind of set up the submissions. So you will do the submissions in CSAMs. Yeah. Any questions about the plans for the labs? So this lab, 2 weeks. It says 1 week, but it will be 2 weeks. Next week, compulsory, obligatory Rust lab. So just basic knowledge about Rust. And then 2 more labs, which are one about programming languages and one about advanced programming techniques. Questions? We'll see how it will go. It is a little bit on the ambitious side, but as I said, you don't have to do it. So it's fine if you don't do it. All right. Today we have a little bit of me whining first, and then we'll look into some ways of doing Rust, and also in some ways of learning in general and programming languages specifically. So please join Menti. The first part is a little bit me being like an old complaining person. And then we'll have a little bit more fun with Rust. All right, let's do it. So, your feelings about Haskell. You can be honest. Autistic. That's a interesting take. Yeah, it's confusing. It's pretty clever. It's interesting, but hard. I agree with all of them. Syntax is unfamiliar, but I kind of like it. I think once you get used to it, you may like it. Yep. Outdated, definitely not. All modern programming languages borrow from Haskell. So definitely not outdated. If there will be new library or if there will be new programming language, you will recognize that it takes stuff from Haskell. There is nothing in the programming world that has not been tried out or already implemented in Haskell, to be honest. Very nice. Yeah, I share your sentiments. So how about Rust? Yeah, that's nice. So hopefully in this lecture, I will show you that your feeling about familiarity with Rust is fake, that it's completely not what you think. But yes, it feels more familiar and it feels more like C++, but it's not. So hopefully after this class, you will sort of understand why it's not. Better than Haskell? Yeah, in some ways, I think it is better than Haskell. But it's also harder than Haskell because you have to deal with memory yourself, which in Haskell you don't have to. And also it's a little bit more picky and a little bit more, it's less consistent. Like Haskell is very consistent. Everything is the same. In Rust, there is a lot of edge cases, a lot of rough things that are not as consistent. But yeah, it's a nice language to learn, definitely. Okay, so what was hardest so far for you in both of the languages, apart from syntax? So let's consider syntax being hard in both languages. I feel Rust has more complex syntax than Haskell, to be honest, but what was the hardest? Monads and state, yeah, totally agree. Functional programming, functional thinking, functional patterns, totally agree. Shifting the mindset, yes, it's hard. Monads are hard. State in Haskell is difficult, definitely. Syntax, yes, but that's we have to live with this one. Concept wise, yeah, I feel those are hard. Faults, yeah. Recursion, not too bad. Tail versus not no tail recursion. Can you spot one versus the other easily? Yep. All right. So what would you like to learn more? What you feel you need to have a refresher? Like what should we cover a little bit more in the rest of the semester? Yeah, async Rust. So when preparing the lab for today, I was because there are some new concepts. So there is this concept of connecting peer to peer, doing publish subscribe or doing client response or request response. Those are kind of new. They are not hard, but they are new. And then both Redis and ZeroMQ offer you an API which is either blocking or non-blocking. And then for using the non-blocking one, you have to use asynchronous Rust. And I was sort of thinking, should we do this or should we split it into two parts? And I decided to split it. So the current lab is used like suggests you use synchronous calls, but you could migrate to use async. But it's a little bit of extra work, right? So maybe we postpone it until a little bit later. Um, so this one, yeah, this one is an interesting take. I'm not sure how much can we do this semester. Maybe we can do some things, but at least for this current lab, I like if you want, you can try it out. You can try to use asynchronous calls instead of synchronous ones. But thinking about it and planning it is it takes a little bit more mental work. Um, Monads. I think whatever we covered is probably enough. You don't have to dive too deeply into monads unless you want to dive a little bit more into functional programming and do more with Haskell. But for the use cases that we covered and for Rust, I think we sort of have enough. This might be a bit too much for this level. Maybe we have to postpone it until next year or maybe master work. Yeah, I will explain the exam later on. All right, so let's do a bit of a quiz. The next question is a bit of a poll. Again, a bit about your emotions and understanding. Yeah, great. So what I am kind of looking for is obviously the last one is every year students have questions, which is great because that means that you know what you don't know, which is good. What I'm looking at are those two. So most of the Haskell material is necessary for understanding Rust, and then Rust adds extra stuff. So those two should be other way around, right? And hopefully in a couple of weeks you will understand why. Yeah, in this lecture we will talk a little bit about this as well. And then those two are like, yeah, personal preferences and kind of our personal biases of what we like, how we are wired to think. And if we do it well, those two should be the same because we shouldn't have a preference, but we do because of the way we learned initially programming. So we try to work on those two to be kind of the same and on those two to be swapped. So after a while, you will understand why and why Rust is harder. All right. So did you read the Haskell book? Pretty good. Better than last year, I think. Um, right. How about Rust? Yeah, definitely better than last year. All right. Thanks for the feedback. Rust setup, you are all using Clippy to whine about the syntax and kind of idiomatic style. You all using tests, including doc tests in Rust, right? And you're automating it with your CI pipeline, right? If you don't, then I encourage you to do that. So make sure that you are committing to your repos. You have a CI pipeline and GitLab, which runs Clippy and runs stuff for you and whines if something is not right. So you should all be using that one. And then a little bit about the programming flow. So with AIs, it is a bit like difficult. So here I'm talking about like your actual mental work. With AI, that changes a little bit. But let's forget about AI for now and let's just focus the way we are doing it without AI. So the first thing you do is you design what you need to do in your head. So you take a pen and paper and just sit and think. And you're thinking, what do I need to use? What do I need to do? Do I need to use a vector or do I need to use a list? Is it a list or is it more like a hash table? Or is it more like a tree? Like what data structure do I need? What will flow from what and how? Like who will be consuming stuff and who will be producing stuff. So you're thinking about kind of abstractions and you're planning abstractly in your head what you need to do. And then you're also asking yourself questions of what you don't know yet. Like what do you need to fill in? So what requirements or what assumptions do you need to make this whole image kind of work, right? So you are making this sort of big abstract kind of thing in your head, sometimes drawing some blobs on the piece of paper, and you're planning your stuff. You're planning the data structures, and you're planning what, after you have your data structures, like what will flow to what and what functions you may need. You don't implement anything yet. So you don't implement until later. Then once you plan this, you write tests. So then you use the signatures and the data structures that you planned, and you're planning the test. You're actually writing the test of how it will feel, to use those methods, what you have to create to have the test written, and so on. And that's great because then you can easily revise. You can go back and say, no, I don't like this method to be returning this. I want this method to be returning this. Or you may go back and say, I cannot have this method or function so big because it's really hard to test. I have to split it. I don't want this function to take so many parameters. I want to change it. So you iterate. So you iterate with those 3 points kind of very quickly and very rapidly because you haven't wrote any code. You haven't wrote any implementation yet. You're just writing the skeletons and the stuff that will plug in together, right? And if you're doing it in Rust or if you're doing it in Haskell, it's really nice because you can use this undefined function bodies and you can return some dummy values and you can sort of play with the skeletons of how it will feel and how it will look like. So you're iterating over the 3 first points multiple times until you are kind of happy with the way it feels to use, okay? And then you write the code. And probably then it's kind of a good way to engage AI and kind of help you to do something. But the first 3 parts, AI usually gets wrong, especially for larger systems. AI is sort of biased towards common denominators. And what you're writing is not a common denominator. Most of the time, what you're writing is something specific to you, like specific to the case that you are dealing with. Unless you're really doing some boilerplate. If you're really doing some boilerplate, then there are well-defined methods of doing the first 3 things, and then you can use what AI suggests. But most of our work will not be writing boilerplate because that will be already written by AI. We will be doing something that goes outside. So we have to spend some time on those first 3 points. So once you wrote the tests and the initial things, kind of you have to make it compile. And making things compile in Haskell, it's like the major task, right? I usually start in Haskell by doing everything is undefined, and I'm just creating the types of my methods or functions, and I'm trying to get it compiled because the types have to match. I haven't implemented anything yet. Nothing works. I'm just kind of making sure the compiler is happy with all my signatures, right? That's all I start with. And once the compiler is happy with all the signatures, the rest is actually easy. The hardest part is to make the compiler be happy with all the signatures. But once you have it done, then you write your doc tests for your functions, and then you write the body. And if the body is wrong, the doc test will fail. If the body is right, most of the time, your program just works. So it has to compile. And then once it compiles, you will have some tests which are failing, and then you're just iterating over fixing your tests. You don't care to do it in an idiomatic way yet. You're just making sure that it compiles and then that all the tests pass. So your code is messy. Your code feels not right. Your code may smell, but it's written, it works, and all the tests pass, right? And only then you start thinking, oh, can I use a point-free notation here? Can I simplify those methods? Can I refactor it such that I don't repeat myself? Only then you do it, right? So you don't care about it initially. You care about it once you have all the tests passed and everything is working. And once you have it done in an idiomatic way, then you say, okay, how slow is it? Is it like really slow or is it acceptable? Like what is like how well it performs, right? So then you consider performance. You don't consider performance early, but you don't do stupid things. So if you can implement something with a single pass over data, why would you do it in 3 passes, right? So this is about the algorithm. This is about your design. So that happens here, right? Your design choices. So if you choose a wrong algorithm, if you use like a linked list instead of an array, that error is very early on, right? And that will influence the performance much more than your coding or the way you actually coding your things. So this point is very important because if you choose the wrong data structures or if you choose the wrong flows, then it will impact the performance much more than anything that you do afterwards, right? if you've chosen a wrong data structure, no matter what you do in your coding, it will be slow, right? So those design decisions you don't want to revisit when you hit this performance bottlenecks. You want to do it early, but once you set on a certain architecture and certain decisions, then you stick to it all the way to this point, and then you may fine-tuning the coding part through the performance considerations, right? You're making efficient implementation of what you've designed early on. But those design decisions, they trump any performance optimizations afterwards. So you cannot make something that is wrongly designed run fast because it is just wrongly designed. Like you're doing it wrong. You're doing it wrong, but fast, right? But it's still wrong. So you want to do it right, and then you want the right thing to be done fast, right? But initially you're doing the right thing, not fast. You're just doing it to work. So this is the typical flow. And this is the typical flow that you will discover once you're kind of working with software for a while. That this is the most important part, and that most important part happens in your head. And my experience with AI is that this part, I cannot trust AI to do right. AI most of the time does that part wrong. It does the coding part right, but not this part. And it can do some idiomatic way of solving things right, but not this part. So the first 3 points from my experience and from some experience online of people kind of talking about AI is that, well, it still is about like us doing it in our heads. So you need to practice that, and you need to train this. All right. So then, where is my mouse? Then if performance is a consideration, so after you've done all of this and you are happy with your Rust code, then you are asking yourself those questions. Do I allocate memory unnecessary? Can I skip allocating memory, or can I reuse memory more efficiently, right? You have to do that for Rust. How many passes over data do I do, right? As I said, those loops and number of passes over data, it's more of a design step, so you should do it early. And then again, data cache and locality, like how is my data organized, and do I benefit from the data being grouped together such that if I'm processing it, it's kind of blobbed together, right? So those performance checklists, some of them you're doing very early on in the design step, data structure and design step, those two first steps. And some of them you do it as a last point, but early decisions kind of impact everything else. So if you screw something here, you have to redo everything from the beginning, right? So when doing Rust, you do have to consider what is about my data locality, data alignment. We talked about alignment last time, and memory management, right? So then you've done everything, you've done the correct decisions, and the program still runs slow. You have a task to do and it takes 3 hours and it's too long. Like the requirement is that it must, I don't know, be much faster. So then what do you need to do? What do you need to do if you implemented everything and your program is too slow or does not perform the way the specification says? What do you do then? Right. So this question is about what not to do. Okay. So you're not doing code optimizations. and you're not doing parallelization. Those are two very tempting things to do, but you're not doing them because you don't know yet what's wrong. You don't know what is slow, which part of your code needs work, right? So you have to do profiling. You have to do profiling first because you have to isolate what is to be fixed. You don't know yet. You just know that your program is too slow, but you don't know what part of the program is too slow, what needs optimization, right? So you're doing profiling. So after you've done profiling, then you will know whether what optimizations you need and whether parallelization is a solution, because often it isn't. Often the profiling problems will demonstrate that the problem is somewhere else and parallelization will not help you, right? So you have to do profiling first. Those two may be suggested by profiling, but may not. It depends what the profiling will tell you, right? Linting we do for idiomatic code beautifications and for removing code smells. And debugging we do for finding bugs. We don't have bugs. Program works, tests pass, it's just too slow. So we're not doing debugging. And doing parallelization or using async libraries depends. Often people jump to this, but it turns out to make the code even slower, right? Because the problem is not with, which is easily parallelizable. So profiling, remember that the activity that you want to do before any code optimizations is to identify what is wrong, right? So what does it mean insufficient performance? We can do CPU profiling. Is it too slow? Like, where is the CPU consumed? What functions do consume the CPU the most? We can do flame charts and graphs of the CPU usage, right? Golang has a very nice support for flame charts. You can play with it, and you can, like, especially with Christopher course, when you're writing some REST server, you can kind of interrogate it and measure like where your server spends time, like what is the most time consuming for your server to respond to a request. So if you're optimizing requests per second, how robust your server implementation is, you want to see like where is the server spending most of the time when the request comes and the response is sent, right? So you can do CPU profiling and flame charts or CPU graphs for this. You can check how memory is used. Do we allocate and deallocate memory very frequently? This affects performance for the CPU, but it also affects how much RAM do we use and how fragmented our memory will be. I/O is often the culprit. If you've done lab 14, you'll realize the problem was I/O actually, right? The problem was reading the file and then parsing it. So reading it and parsing it. Can you parallelize this part? You can parallelize the processing, but reading a file and parsing what you're reading is kind of hard to parallelize. You would have to have multiple parts reading the file from multiple starting points. And then it is actually very difficult to do it in an efficient way. So I/O profiling, like if your profiling tells you that the bottleneck is I/O, then there are different ways of dealing with it than to CPU bottleneck, right? You're identifying where the bottleneck is. And then cache misses. That's a very more in-depth analysis of why your processing pipeline is slow. And every time you have to invalidate your cache line and reread the cache from the RAM, you're losing 10 to 100 times performance, right? Every time you're processing something from within the cache, it's 10 to 100 times faster than if you have to read it from RAM or from, God forbid, disk, right? So cache misses profiling is another profiling tool that helps you to identify what is that you're doing wrong. And then based on all those tests, based on all the information you can gather, you decide what to do, what you need to optimize, what you need to change. Sometimes you will have to go back to your design decisions and say, oh yeah, I have to organize it differently, right? There is this very we will have a lecture later on from Per Morten, and he will tell you like what he's doing to optimize his performance for the tasks that he deals with. But there is a very common pattern that you have to keep in mind. So one, it comes from kind of object-oriented programming, and one is called array of structs. So that's number one, and that's most of what people use when they think about designing OO, because they think, okay, I have a class person, right? So I have a class person, and then I have some attributes, and then I have some sort of a collection of people, and then you're basically doing number one. So you effectively have some sort of array of structs, right? And that's most of the time what we do with OO. But that pattern has a very bad cache locality, and it's very bad for optimizing performance if you have to do something on a specific field, right? So for example, if the specific field of the person is a salary, and you have a lot of processing to do with salary, calculating taxes or doing stuff, then this type of array of structs is very bad, because every time you need to read somebody's salary, you have to invalidate your cache line because your struct occupies your cache line, right? So for each person, you're missing the cache because it's, it's filled up with some unnecessary things which are not used for you, because the only thing used for you is a salary or maybe like a tax rate, right? If those two things are useful for you and it has multiple fields which you have to read every time to get those two, then your cache is filled up with rubbish that you don't use, right? So there is a second pattern, and the second pattern is called structs of arrays. Okay, it's the upside down, reverse of this, right? So instead of saying I have a collection of people and each person is a struct, what you would do is you would say I have a struct which is so I have people collection, which is my struct, and this people collection has a salaries, which is an array of all the people's salaries, and tax rates, array of tax rates of all the people tax rates, and names, whatever the fields are here, right? Whatever the fields are here, you put it here, but instead of having one value per person, you have one value per person in an array, right? And what it means is if you have to process salaries, all you do is you get the pointer to this array of salaries, it goes into your cache, and suddenly it's all in cache because it's one next to another, right? So if you're processing and calculating something with your salaries, it's just like a dream. It's like one after another. You don't have to invalidate your cache line, right? So those two are very important to remember, because we often do stuff this way and it just makes stuff slow, right? It's inefficient. And it's as easy to do it this way, and it will make life much easier, right? So doing it array of structs or struct of arrays are two models that we can kind of play with and make a design decision of doing one over the other, right? All right. Let's go a little bit further. So then with async. Async is a great topic, but it's a difficult topic, and it has two aspects. One aspect is that we're doing things concurrently because it makes sense from the design decisions. Like we want certain things to be considered independent of other things because it makes the design better, right? So for example, if I'm doing a game and I have to interact with the user and I have to calculate the physics of my environment, I don't want to be thinking about those two at the same time. I want to say, I have a loop which deals with user input, and I have a loop which deals with physics calculations, and they happen at the same time, right? So I'm kind of doing things concurrently, but concurrency does not mean parallelism, right? I can have still single thread, and I can still be doing those two things, but I'm not actually doing them in parallel. I'm just like thinking about it in an independent way. And we often make those decisions for, so this is concurrency, right? Concurrency versus parallelism. So those two are not the same. And the concurrency is often a design decision, because it makes our designs better. It makes our groupings and encapsulation and things better. This one is mostly about performance and about architecture. So it's about cores. It's about like CPUs, how many CPUs you have, how many cores you have, nodes, like if you have multiple machines doing certain things and so on. So this one is about distributing computing across multiple parties, actually physically, right? So this is about mostly performance, but distribution, performance and distribution. We often do this first. We do concurrency, and then we make the concurrent system parallel because we kind of deploy it on multiple cores, right? But they are not the same, and they are done for different reasons. This one is done to utilize the hardware better. This one is done to make our designs better. And then you have to think, do I need it? And why do I need it? And which level do we use it? Like, do we really need to make it parallel because of efficiency or performance? Or do we want to make it concurrent because it makes our groupings or logical considerations easier? So then what are the options for the processing pipeline? And if we are parallelizing something or making things actually done in parallel for performance reasons, is the work per item big enough, right? If I have to do addition, as it was with task 14, the addition is such a trivial task that parallelizing it makes it slower because of the overheads required to spawn the jobs and things like that, right? So those of you who did lab 14, you kind of know that the bottleneck was I/O, and then the task of counting the summing up the X was like too trivial to be parallelizable, right? And making it parallel would make it actually slower than faster. So we have to make some considerations. One thing that is not here is also an interesting concept. So remember about those two. And one to remember is, so if we have, let's say this is time, and I have something to do. And let's say I have those 4 things to do, and they take, let's say 1 minute, right? So I have, if I start it, it will take 1 minute, okay? So then if we say those tasks are independent, I can do them concurrently, but also in parallel. And then we kind of do them in parallel, right? And I will have a little bit, so I'm kind of starting here. I'll have a little bit of overhead of like wiring things up, right? So I will, so if that was 20, what was it? 1 minute. So 1 minute divided by 4, 15 seconds. So if this is like 15 seconds here, then it will take me a little bit more than 15 seconds, but much less than 1 minute, right? If I do them concurrently. or in parallel, right? Concurrently does not mean they will be faster, but if I have 4 hardware threads, if I have 1 CPU and 1 core, then doing that will actually take more than 1 minute because I will have to context switch and I will have to do them concurrently, but not in parallel. But if I have 4 hardware cores or CPUs, and I can actually do them in parallel, then an expected result is somewhere a little bit more than 15 seconds and much less than 1 minute, right? But what happens if I cannot parallelize it? So what happens if I have to do task 1 before task 2 can be done, and then task 2 before task 3, and task 4 after task 3, right? So now they are dependent. Can I benefit from an architecture that has 4 cores? So on a single core, it takes 1 minute. If they are independent, I can benefit from four cores or 4 CPUs by parallelizing it and making it faster. But if they are dependent, can I benefit from 4 cores? Not really, right? So there are 2 metrics. One metric is called latency. Latency means if I start, how long do I have to wait for it to finish, right? So it's like start to finish. Okay, so that's latency. And for latency, if I have 4 cores with this particular case, which is dependent on one another, I cannot do anything. But there is another metric. And the other metric is called throughput. Throughput. There is a O somewhere. Throughput. So what throughput is? So latency is time from start to finish. What is throughput? So it's request per second. It's a metric which measures how many things can I get done in a unit of time if I'm repeating the same activity over and over again, right? So when you're sending a packet to a server and require a response, so if you're doing a cloud computing and you build your server and now the client connects, you have to do processing and you send the client a response. That's latency, right? So the client says, okay, that took 10 seconds, right? So request, processing, response, and the client was measuring time, and it took 10 seconds. So latency is 10 seconds, okay? And now one client connects, another client connects, another client connects, many clients connect, right? And then you are taking 10 seconds to respond to the first one, but how many connections, how many requests can you process per second overall, right? That's throughput. So your latency might be 10 seconds, but your throughput might be 1,000 requests per second, right? That the first, like, they will wait initially 10 seconds, but you are processing 1,000 requests per second, right? You get the difference? So we cannot help with this particular case. We cannot help with latency, but we can help with throughput. So what we do with throughput is we do this. We say, okay, let's do this. Let's put task 1 on core 1, task 2 on core 2, and so on. So we will use 4 cores. Each core will be responsible for just one task, like one part of the task, right? So it will just do this. And when the request comes, it will spend 15 seconds doing the first, so 15 seconds. It will do the first part and pass the result to the second core, right? When after the first 15 seconds, it passed the results, then it can start processing the second request for the first part of the pipeline, right? So before I had to wait 1 minute before I could process the second request, right? Now I have to wait 15 seconds before I can do the second request. My throughput has increased 4 times, right? Because before I had 1 request per minute, now I have 4 requests per minute, right? Because I'm using 4 cores. You see the difference? So remember those two concepts, the latency and throughput, they are not the same, they are different. And even for sequential tasks, you can benefit from a multi-core architecture by increasing the throughput. You will not increase the initial latency because the client which connected will still have to wait 1 minute to get the response. But now you are processing 4 requests per minute instead of just 1 per minute, right? You quadrupled your throughput. So we have a little bit less than quadrupled because there is always a little bit of costs, right? Of setting things up and so on. All right. Any questions about this one? If not, let me check the next slide, and I think we should have a break. So we talked about it, memory CPUs and multiple CPUs and concurrent versus parallel. So that's super important. All right, so let's have a break because the next one is about idiomatic patterns. So we can make a 10 minutes break. All right. Right. So where we were here. Yeah, so I've added an announcement for next week, Oblique. And we doing the Rust idioms. So what is a collection? So if you were to explain to someone what is a collection, what word would you use as um, an alias? Yep. So we often think in terms of lists. We say, yeah, a collection is a list, but that's not true. It's partially true because a collection can be a tree, right? So what other word would be good to use? Grouping, yeah. What else could you use? Storage usually means like persistent storage. We often don't use the word storage to call things in memory, but we often deal with collections in memory. But yeah, but you could say, but it doesn't capture the essence. What word would be a good word to describe what collections are? Yep. So array or a list are example of correct collections. Yeah, that's a more wordy description. Great, a container. That's the good word, right? So collections are containers. We're dealing with some sort of containers. So remember that. Remember that when we're dealing with collections, we have some sort of container which contains stuff inside. It can be a list, can be a tree, can be a array, can be a hash table, right? Okay, so container is a good abstraction. So what example of collections do you use often? Lists, arrays, vectors, maps, structs, array lists, trees, linked lists, perfect. So those are the collections or containers that you often use. Queues, yep, very nice. So then think of what you're using them for. Nice. So there are kind of two perspectives here in the answers. One is that we're using containers or collections to store something, like we have a bunch of people, we have to store them somewhere and then access them for processing. So that's where, simple storage, storing. And then we have an answer which says it's a grouping, like we group things together such that we can operate on it as a single entity, right? So this one is more kind of a design perspective where we say we group things in order to treat it as a unit, as a single entity, right? And that's very important. So we came from C and C++ using simple vectors and arrays as a store, which has been iterated over with for loops and things like that. And through other languages and through other concepts, we kind of said, well, containers are not only for iterating over things, but they kind of form for us a unit which we can process as a unit, right? As a single entity. And that's a very important perspective. So this perspective is something that you need to remember and kind of try to think more often when you're planning to use containers or collections. So then what functions do you use on collections? Yep. So we can map things in the collection. We can insert, pop, we can iterate over them. And then in functional programming, we had some other concepts that we've used also to be applicable on containers or on collections. So different languages offer different vocabulary to deal with collections. So this is like a very hand-wavy question of you trying to map how many different functions a language offered to you for managing and accessing collections or processing collections. So how many different functions or conceptual frameworks you were given in a language to deal with containers or with collections. You can build your own containers and you can build your own collections very easily, but the languages tend to offer a certain amount of predefined collections and predefined vocabulary that is offered to you. And this question is about this vocabulary, like how many different things can you do on containers? So for example, can you fold things? Or can you fold left and fold right in a language? Which languages offer you the choice of folding left or folding right? Which languages offer you folding at all? Can you do folding in Golang? Not natively, you have to implement it yourself, right? How about mapping over collections? Can you do it natively in a language? Yeah, in most you can. In C++, you can't, right? I mean in C. In C++, you can. Can you flatten a container? What does flattening a container means? Is that concept available to you in a language or it's not? Can you flip the container upside down? Can you have a container inside another container and flip them? Can you do that in a language? How is that operation called? So different languages offer you different kind of vocabulary and strength. And Haskell is definitely like on the top. And C is definitely on the bottom, right? C is sort of the most low level. You basically have a for loop. And Golang is not far behind. You have a iterator in a form of a form loop, although Golang has iterators, which allowing you to iterate over contents of collections without having the counter, for example. Whereas in C, you cannot do that without a counter. So as we sort of navigate this hierarchy, we can kind of see that Haskell is sort of on top. And Rust is not far behind. Rust has a very rich vocabulary for dealing with collections and containers, and you have to get used to it. And it is much more similar to Haskell than to C++, which we will see in a moment. So we have various collections like vectors, strings, hash maps. Some languages offer us generics, some didn't. Golang was initially designed without generics, and the community was pushing towards addition of generics into the language because the community felt a language without generics is really handicapping the developers. So they've added generics into the language. So Rust is no different. You have those primitive things in Rust too. So you can declare vectors. You have a type specifier of what the vector contains. You have simple methods for adding elements. And then what can you have inside a vector? So in this case, what do we have inside a vector? What this vector contains? Yeah, 1 and 2. And what is 1 and 2? Yeah, integers. Probably I32 inferred type. So those are integers. How they are stored here? Are they stored by reference to integers or by value? By value. So we can store values. Can we store references to stuff and vectors? Yeah, we can. And then we have those boxes. So a vector is like a box wrapping something inside, right? And then Rust manages the ownership. So if the box contains values, the box contains, like, owns the values, right? But if the box contains references, you have to deal with the ownership in Rust, like who is responsible for managing the ownership. Then you can read elements, same as you are doing in C++ or C, by the square brackets, right? Have you used this in Rust this way? Yep, you can. What's wrong with using access this way? What can happen? Yep, you can use an index of an element outside of range. So you may try to access something which does not exist. And what will happen then? Bad things will happen. Kittens will die, right? Your program will crash. You'll have a runtime exception and your program will crash. And we don't like our programs to crash. So we take a lot of effort making sure we don't access stuff outside of range, right? And that's why Golang introduced iterators such that you don't have this index. You just say iterate over all the collection items and you get the reference to the item, and you cannot go outside of the range because it's built in to not ever go outside of the range, right? But in languages like this one, if you're using this way, you can go outside of the range, and then bad things will happen. So we don't use that this way in Rust. Even though it is possible, you're not supposed to do it this way because it's not idiomatic. So what does it mean it's not idiomatic? What is idiomatic use of language? It's a set of patterns or design principles that are encouraged to be used. You can go outside of the idiomatic way. So you can code it this way. But it is considered not nice or smell bad because it exposes you to potential bugs or failures that we don't want to have in our code. So idiomatic way is not to use it through indexes, but to get elements with the get method, right? So the get method returns you a value in a box. And if you go outside of the range, it will not panic. It will not throw a runtime exception. It will simply return you none, right? It will tell you that you went outside of the range, that you have unhappy path, right? We want our processing to be always on the happy path, but this mechanism allows you to say, yeah, something happened. Like we have the unhappy path now. Like somehow we went out of the range and we are in the unhappy path. Deal with it, right? So it will not panic. It will not crash your program. It allows you to deal with it, right? Should we always do it this way? What is the cost of doing it this way? Extra method call, right? There is an extra method call for wrapping it and unwrapping the value. So if you're processing your machine learning arrays or vectors and you're dealing with millions of operations that you have to compute, you don't want to do it this way because it will incur a considerable cost on your processing, right? But you have to make sure that the indexes never go out of the range. So if you can assert and make sure that your indexes never possibly go out of the range, or if they do and the program crashes, it's like nobody dies, sure, you can access the memory directly by an index. But if you're not sure, or if there's severe consequences of your software crashing, like you're building something, a server for serving requests, or building something in financial domain or medical domain where you cannot allow your program to crash, then you should just always do get, right? All right, so there is a variation on the get, which combines the matching of what we got, such that if the index is out of the range, we have kind of an error case, right? And in this particular case, it is an error case because we only have 3 values, but we are accessing the value out of the range, right? So how does that code look like? Is it good? Is it idiomatic Rust? What do you think? Yep. It's pretty normal to have code like this where you're dealing with the happy and unhappy path, right? But it feels a bit verbose, right? We learned that if we have to do match and if we have to do if statements, yeah, it feels there is a better way of coding. We would like the unhappy path to be taken care automatically for us and the happy path to be the code, right? So if we can code in a way that deals with the happy path and the unhappy path is sort of taken care of by additional mechanisms instead of us verbosely doing it, it's usually better, right? So let's see if we can do it better. So this one is a match which deals with the happy and unhappy path. And this one is if let, which deals with the happy path, but the unhappy path is sort of in the non-existing else clause, right? So here we basically saying, well, you know, if everything is fine, we doing it, but if something went wrong and we outside of the range, we ignoring it, right? Should you do that? Yeah, sometimes you can do that. Sometimes, you know, when you're expecting user input or when you're doing something that does that require you to ignore it, you can do this code, right? I'm writing now like a peer-to-peer system for file sharing, and it has a certain protocol, and the protocol can be abused. So some other nodes can kind of post messages, which you just have to ignore. Because if you start processing them, they can do denial of service attack on you, right? So in this situation, I'm dealing with like parsing, and then if something is out of like, is not correct, I'm just saying, yeah, I'm just ignoring it. I'm doing nothing, right? Because dealing with it would cause me to spend cycles and expose me to a potential denial of service attack. So this code, yeah, it's okay, but you have to be cautious that, you know, you don't want to do it always. Like sometimes you need to know that there was an unhappy path and you need to deal with it. If it's user input, you have to say, hey, you've entered it wrong. You kind of doing something wrong. So useful patterns and useful idioms. We try to avoid sentinel values in Rust. We try to use option and result and happy and unhappy path, as we discussed in same as with Haskell. And using match and if let is a very common pattern in Rust. So this code, like if let with an option or a result and match with an option or a result are very common patterns, right? Um, 。 Iterators, of course, you should use iterators in any language that you have that has them. So here is a simple point struct, and here is a function. So we have a point with 2 coordinates, and then we have the constructor, and we have a function which calculates the distance between 2 points, right? So this function calculates the distance between the point, this, and a point which is passed as other, right? So we have Cartesian distance calculation, which calculates a distance between 2 points. The one which we kind of defined here, and the other one which is passed as a parameter to the distance function. And it calculates a floating point number as a result. Anything unusual in this implementation? Any kind of complaints about this one? No, looks pretty normal, right? Pretty fine. No code smells. It looks okay. So then we want to calculate distances over several points, right? So we have a vector of 3 points. So now I have a container, and my container has point 0, 0.1, and 0.2, and I want to calculate that distance and that distance, right? That's my intent. My intent is to calculate distances between points, and I have some sort of vector or array or a list with my points, right? And I'm doing it this way. So I have my input. So my input is this vector, and the transformation should give me another list of distances, right? So this distance is here, this distance is here. So this is the distance between those two. This one is the distance between those two. Make sense? Okay, so is this code something you would write in C++? So who would write code like this in C++? What else would you write? Like, how could you improve it in C++? We kind of need to go over the iterator because we need those 2 indexes, right? We have to have the current point and the point next to it. So the metaphor by using the indexes in C++ is quite fitting. So will this work in Rust? It should work, right? But it's not idiomatic Rust. It's C++ Rust. It's a Rust that you should not write. So we have to improve it. So here is an improved version. And the improved version communicates the intent of what we're doing much better. But it's very unfamiliar to a C++ person, right? So if you look at this code, you will be faced with several unfamiliar concepts. One unfamiliar concept might be mapping, right? We say like, why we mapping, right? But that's what we do. Like, we basically mapping, we have one domain, we have to do the distance calculation and map it to another domain. Like every time we're doing something like this, it really smells like a map, right? We're mapping this to this. We're mapping points to distances, right? That's our intent. Do you see that we're doing it here? Do you see that we're doing the map? Yeah, we do, but it's a little bit implied. The map is sort of inside the for loop with this distance calculation, right? And then we pushing the, like, within those two lines, we're doing a lot of things, right? We getting the two neighbors, we calculating the distance, and we collecting the results into a distances response collection, right? So those two lines of code are doing multiple things, which are like you have to decode it of what is going on. You have to sort of read it, stare at it, and understand what's going on, right? Here is like I'm mapping a function and then collecting the results. It's like in your face. And then getting the pairs is the sliding window which says, get the pairs for me, do the map, and then collect the results. So reading this code, once you're familiar with Rust, is much faster and much cleaner and much easier because it's like in your face what's going on, right? Here, it's not obvious. There might be different things going on. Like you may be doing really different things here. You really have to read every symbol carefully, every index carefully to understand that it's actually doing what it's supposed to do, right? If you have one typo somewhere here, one symbol is wrong, like this I, or there is no +1 or something is like messed up, you're really in trouble. Like you will not get the behavior you expect, right? Here, you have those two symbols that could be messed up because we're taking the pairs of points and we have to reference them, but the compiler would complain, right? If you mess up here, the compiler will complain that you are doing something wrong. And the clarity of what's going on is like really clear. We have a collection, we're taking a sliding window of 2 points, we're sliding, we're mapping, and then we're doing collect, right? Have you seen code like this? Have you seen code with map and collect before? So if you're doing JavaScript or if you're doing Rust, you will see it a lot. This is a very common pattern of doing something and then collecting things into a final container, right? So we're doing some transformations, and then we're saying, okay, whatever the results are, put them into that container. So this pattern is very common. The sliding window, yeah, it's a little bit less common because we often do map over a single item, right? You've learned this before in Haskell. We often did map on a single item. We transformed one list into another list, like one item at the time. But what if we have to transform a pairs? Then, yeah, you have to do some tricks. And in Rust, you do some tricks, and you basically have a Windows facility to see how big the sliding window is, right? You need to learn this because this is idiomatic Rust, right? This is how would you do it in Rust. This is how would you do it in C++, right? You don't have this rich vocabulary. You don't have this concepts. You usually just do this. In C, you do this as well. But in Rust, you have to do this. And it's not intuitive. Like you basically have to remember that there are things that what we want to do. Like we want to take pairs, we want to map them and then collect, right? So once you kind of design it in your head, then you kind of know like what needs to be implemented, right? So we may have some edge cases. So this is a student struct, just name and age. And then we have an implementation of increasing the student age by a certain value, and the age is in years, right? So we have unsigned integer, which goes from 0 to 255. So in all normal circumstances, that should be fine, right? But what can go wrong? In this particular case, what can go wrong? So what assumptions are we making here? Yep. Yeah, that's one assumption. Yeah, what other assumptions are we making? For example, or live longer than 255 years, right? What will happen if there is some sort of freak which lives longer than 255 years? We will have an overflow. Like this function will give an incorrect result, right? It's an edge case. So we have to deal with the edge case, right? So how can we deal with the edge case? Well, we basically have to deal with it by recognizing that this operation may fail, right? So if we design that the student cannot be more than 255 years, and we do have this freak edge case, which in this particular case is just made up, but imagine that you're dealing with some account balances or something that you're making an assumption, right? You're making that assumption that no computer will have more than 65K RAM, right? Bill Gates made an assumption at some point, which turned out to be like wrong, right? What happens after that? Like, what happens if something is bigger than what you assumed? Well, you have to find the edge case, right? So in this case, what we said is, right, like if this happens, overflow happens, and we have a bug in a system, right? We have a wrong value, right, in a system. So we have inconsistent data. So in this case, we said, no, we will deal with it. We will recognize if we add the years to a student and the result is smaller than the current age of a student, that means we had an overflow, right? It means something went wrong. Like if we increasing an age of a student and it end up with less age, that like we have an overflow. So we say, okay, if that happens, we return none. Otherwise, we do this, right? So again, we have a happy path. I mean, happy path in the else and unhappy path in the if. Will it work? Yeah, it will work, but it's an ugly code. It's ugly for many reasons, but one reason is that we mangled happy and unhappy paths together, and we also doing a manual check of the overflow, right? We're doing a little bit of a manual check of overflow, and in certain edge cases, even this may kind of not work that well, right? Because we might be on the limit of the 255, and we may have a certain value that kind of flips it in such a way that we end up with a wrong value, but bigger than the original value, right? This check is not bulletproof, right? It works most of the time, but it may not be bulletproof. And if there are built-in mechanisms, we should use the built-in mechanisms, right? So let's use a built-in mechanism. And the built-in mechanism is checked add. So checked add basically adds an integer to another integer. And if there is an overflow, it will return none. But if the addition is correct, it will return the original sum value, right? So it basically is doing what we try to do by hand. There is a function which does it, which is built into Rust, right? So Rust has a checked add, which basically returns an option, and the option will return none if there was an overflow, and it will return some if the addition was fine, right? So now we have this code which says, okay, if everything was fine, then we have we return the student, and otherwise we return none, because we are kind of letting the monadic or the student which is obtained by doing those operations to be the one bound by this let, and then we kind of return it. So we fixed one thing. We fixed this manual check by the checked add. But the code is still ugly, and the code still smells like it's a mess, right? It works, it will work fine, but the code is not something that we should write. So how can we fix it? Well, we can just do this, right? We don't need this binding. Like we don't need it. Like in Rust, you always return what is the last thing without the semicolon. So you should use it. It's idiomatic Rust to do this. Binding to things that you don't need to bind to things is kind of not idiomatic, so you should avoid it. So this is the way you should write it. Can you write it like this in C++? No, you can't, because C++ does not have this like last thing in the context without the semicolon is the value that the context returns. So in C++, you probably have to do this, right? You have to bind something and then return it. But in Rust, you don't. You do it this way, right? This code is better, but it's still ugly because we still deal with happy and unhappy path with the if statement, right? Every time we have to use if statement, we increasing what? The cyclomatic complexity of our functions, and we don't want to do that. So we should avoid this. So how can we avoid this? Well, you've learned in Haskell that we have those boxes and we can do stuff on the boxes and we can isolate the happy and unhappy paths in such a way that a function which kind of is doing something on the unhappy path shortcuts and kind of exits to the return type, right? And we can observe that our return type is an optional student. So if something goes wrong, it will naturally render itself to an implementation which shortcuts to none being returned without us doing it explicitly, right? So if we have to write it, then we're not taking benefit of this mechanism, which we already know, and we should rewrite it to a mechanism which takes kind of effect from it. And one is map, right? We know map. So map is not only for collections in a form of multiple items, but it's also for boxes. So here we have an optional box for student. We're doing this checked thing. And if it returns something, we mapping this new age function to the student, which this kind of returned. It's like, so student is not inside the box, but checked add will give us a box of the age, which is either none or a number. If it gave us none, it shortcuts and returns none upstairs. If it returned us a number, which means we didn't have an overflow, we're saying, okay, the student age is the new age, right? Can you read this code? Do you understand what this code is doing? So student is not inside the box. Student has an age attribute, and then we adding years to the age. It can overflow. If it overflows, this call checked add returns none. And when this call returns none, none is returned to the upstairs, to the caller, right? We are done. We are in an unhappy path. If this call returns some value, the value is wrapped in the sum, in the option. And we can unwrap it by a map because we can go inside the wrapping and get the value through a map. So we're getting the value. The value is called new age and it's U8. And then once we are here, we have a context which the map is applying to student because we can do it, right? So we're changing the age of the student. And then we are returning the student because we are inside the map. So after the map is done with us, it will wrap the result into the context it was in, which was the option, which means this student will be wrapped in sum and returned here as an option, right? It's all Haskell. It's like the same with the maybe type, right? It's exactly the same. That's idiomatic Haskell. You cannot do that. I mean, you can do it in modern C++ because they do also introduce optional things similar to that mechanism, but it's very like not non-idiomatic in a sense, right? In Rust, it's very idiomatic. You're supposed to write code like this in Rust, right? Is it intuitive for a C++ developer to write code like this? Not so much. Is it intuitive for a Haskell developer to write code like this? Of course, because it's exactly the same, right? So you will notice that Rust deals with all those boxes and all those methods to deal with things like map and checked add and a lot of like option and sum and matching. And it's kind of like Haskell all over again. And you're supposed to use it this way. You're not supposed to do C++ with Rust. You're supposed to do Haskell with Rust. And you're supposed to avoid unwrap, isSum, or any unboxing functions that you typically do to force Rust to behave as C++. You will notice that when you're doing Rust, you always want to say unwrap, get me the value, unwrap it from the boxes, right? You're not supposed to do that. You're supposed to use methods which deal with happy and unhappy path and boxes in a way that you learned from Haskell. So there is so this one will work. It uses map, but that's not the only way you can write this code in Rust. Rust has also something which is called and then. And then again is a little bit counterintuitive, and it's not that yeah. So let's go back here. So here we can see that we have a student which is not optional student, right? But this function increase age returns as an optional student. So it can fail and it can return none, right? If adding an age to a student is pipelined with something else that can also fail, it would be very nice if we can pass optional student to this function, right? But if we pass optional student to this function, we cannot say student.age anymore because student is inside the box, right? It's inside the option. So we could do unwrap, but we know we should avoid unwrap, right? So we cannot do that. So if we pass the optional student to the increased age, then we have certain functions on top of option, which we're supposed to use such that we don't use unwrap, but we deal with the happy and unhappy path in the Rust way. And the way to deal with it is this and then. So if student is none, and then returns none to the caller. So it's shortcuts. So if we pass none here, then it says, okay, none, right? We're done. We are on the unhappy path. If we pass some student, then will get us, it will look inside the box. It's kind of like map, which looks into the box, gets us the value, and let us do something with it, right? So here we get the student directly. So this student is inside the box. This S is the actual student, is the reference to the mutable reference to the student. And then we can do something with it. And what we're doing with it is basically what we did before, right? And then we're returning S, which then wraps again in the option and returns to the caller, right? So the most Rust way of dealing with this edge case is to say, okay, we may have an edge case. If we have an edge case, we have to use options because they can help us to deal with the unhappy path. And if we keep passing and returning options, then we have certain facilities which are similar to Haskell, which allows us to grab the value from inside the box, do something with it, put it in the box and pass it along, right? And that's what happens here. Would you write code like this immediately coming from C++? Definitely not, right? And that's why Rust is hard. Rust is hard because this code is very non-intuitive to a C++ programmer, but it is intuitive to Haskell programmer, right? Dealing with those boxes with maybe types and optional types, it's like bread and butter. We always do it this way. And dealing with maps is like you know it from Haskell already. But now you have to learn all those extra methods which Rust gives you, which are non-intuitive. Like you wouldn't guess that there is an and then method, right, on top of option. You have to go to the Rust documentation and check what can I do on options. And then you can see a plethora of different operations that Rust gives you, right? And that's why I said Rust is harder, because in Haskell, you only need to remember there is map, fold, and so on, and that's it, right? They work for all the types. In Rust, you don't know what works for option, and you don't know if the method and then on option is the same method that is on the result. Result is the same kind of applicative, but you don't know what Rust gives you. Does Rust gives you and then for result as well? You don't know. You have to check in the documentation. So there is more checking and more learning that needs to happen with Rust, because Rust is like more verbose, more manual. It uses those facilities in a less generic way. Haskell uses them in a very generic way, and it's less to learn. You just need to learn one concept and one kind of function, and then it's kind of reusable, right? So your mileage will vary, and your speed in adapting Haskell in Rust syntax will vary, but concepts are the same. And you always have to think on, when you're doing this design stage, what are you designing? And like in the functor and applicative ways, because they kind of give you the bootstrapping that kind of allows you to benefit from idiomatic Rust. And it's not easy. Rust is considered one of the harder programming languages because of this, because of those heavy concepts that it borrows from Haskell. It has functions like map, or, and then, like once you start using them, they will become your second nature, but there is more vocabulary to remember. So I don't remember all of those methods. Like when I have a break from Rust, I have to like go and kind of check which one was it, which one was the one which I want. All right, so the final thing about this lecture is how to learn Rust. And it's kind of hard. So you need to know what you don't know to be able to learn it, right? So you cannot learn something that you don't know existed. So you have to expose yourself to things that are beyond your current vocabulary or your current kind of frame of reference. So in Rust, it's very like that, because you think Rust is fine because you can do C++ in Rust, but it's not. Rust is different. Rust is much closer to Haskell than to C++. And you need to kind of adapt that way of thinking and that way of doing Rust, because that's the idiomatic way of doing Rust. So this quote is from a lecture, which I will skip to the lecture, which talks about how to learn Rust. And it's a little bit, it's a 50 minutes lecture by a Norwegian developer in the developers conference. It's really fun. Like if you're on a geeky site, he's quite funny. And the other thing is that you kind of learning by different things being done at different times and at different pace and in different ways. And in many times, we learn really well by failing. So if we try something and we do it wrong, we remember that we've done it wrong because we've done it wrong. So failing is kind of part of learning, and it helps if you develop this sort of a sense of having fun from your own failures, right? So every time you have a bug and you spend 2 hours on finding the bug and you find it, there is a natural endorphin injection which says, okay, you solved it. You kind of spend time looking for it, and you should cherish it. You should don't be kind of upset that you wasted 2 hours. You should say, great, like I fixed the bug, right? And if you develop this kind of self-gratification from failure and then like fixing it, you will have a much smoother sort of learning process. So the lecture, I will post so there is like a book called Why Failure is a Good Thing. And there is this lecture, and the lecture is quite fun, and I kind of encourage you to watch it. It talks about Rust, but it mostly talks about him coming from C++ and thinking he can like master Rust because he already knows C++ and learning the hard way that that is not the case. So for C++ developers, this is a kind of a fun lecture to watch, but it's also a fun lecture to watch because he talks about learning in general, like how we learn and what the research suggests. And for those of you who will not watch it, because I'm sure you all not will watch it, the main point is that doing multiple things in a very disorganized way teaches you much more than doing very systematic one thing at the time tasks. So he gives examples of different sports and different learnings and different examples of experiments where people were either practicing in a very systematic and very kind of box-oriented way versus people which were kind of doing a very chaotic and very jumpy kind of learning. And every single time, the very jumpy and very kind of unsystematic and very disorganized way of learning proved to be much better than the organized one, which is contradictory to what we feel. We feel if we read the book kind of chapter by chapter in a very organized way, we feel we learned more than if we read a couple of sentences from this page or from this page and from this page. But the research suggests that the effectiveness of learning is actually much better if you do it in a disorganized way than in a very systematic way. But our perceived benefit is the other way around, which is weird, but that's what the research suggests, right? So if you feel like you're not going anywhere, if you kind of you wander from like task to task and you're jumping from help page to another help page, don't worry, like the learning is happening. Even though you may feel you kind of not doing it in a systematic way, the learning will kind of pay off. So this is like a homework, an extra lecture to watch. And I, as I said, he's a Norwegian developer learning Rust, and he came from a C++ background, so he went through what you are going through, and he has some interesting insights on learning in general. So I will finish here. I will post the slides onto the wiki, and what you will try now is you will try to set yourself into this chat task 15. And if you have questions about Redis or about ZeroMQ on a conceptual level, you can ask me. And I will spend a little bit of time talking about it next week before the Rust Oblique, such that we catch up. Because I thought you had some socket programming before, but if you didn't, then I will talk a little bit to because you will spend a bit of time like catching up with the networking part, right? So yeah. Any questions? Okay, then thanks for today. And as I said, we are here if those of you who want to tackle the lab 15. We don't have any deadlines, right? All the labs deadlines passed. Is anybody wanting to have a deadline extended for one of the later labs? Like you wanted to do it, but you didn't do it because it was for whatever reasons. Do you want me to extend any of the deadlines? Yeah, which one? Okay, so 13 is the finding a number divisible by other numbers. So that one is a smaller one. 14 was quite big. It's yeah, 14 was quite big because, I mean, the task is quite simple, but then doing all the performance thing is a bit time consuming. All right, so I will extend this one to next week. Any other requests? All right. So let me do this then.